Okay, well, I'm in a classroom and there's some construction going on next door, so there's probably some extra noise in this video's background, but it is what it is. We're trying to sketch a rational function, and I'm trying to make this, just one of the ugliest rational functions I could possibly create. I literally just put this together, tested that the that the y-intercept was, somewhere on our axis, and haven't really done anything other than that. So who knows how this is going to end? And let's see if we can sketch this thing, because we should have all the tools to be able to sketch this ridiculously complicated rational function. Now, those tools, it's a 4-step process, right? And it doesn't matter the order of these steps. We just need to find 4 things. We need to find end behavior. And that comes from the ratio of the leading terms, right? We're going to be examining the ratio of leading terms. And so that would be that a sub n x to the n. Oh, let's get rid of that. So a sub n x to the n, and then divided by b sub m x to the m. And that will be that ratio of leading terms from our general definition of a polynomial. Okay, and so then the second non-ordered thing that we need to find would be our y-intercept. And we find that by just setting by evaluating f of x at 0. And that'll give me the y-intercept. Then we need to find our x-intercepts. And we do that by taking my f of x, setting it equal to 0, and solving for x, which in practice really just means take the numerator, set it equal to 0, and solve for x, because the first thing you do in that situation is multiply both sides of the equation by the denominator. Okay, and then the 4th thing that I want to do here is determine my domain restrictions. And remember, they are either removable or non-removable discontinuities. And that comes from whether or not I can cancel the 0 out of the denominator or not. And so the question I have to ask myself is, can I cancel the 0 out of the denominator? If I can cancel the 0 out of the denominator, then it was a removable discontinuity and it's a whole. If I cannot cancel the 0 out of the denominator, then it's a non-removable discontinuity and it's a vertical asymptote. Okay, so those are the 4 things that we're equipped to look for. And remember, we're not going to look for oblique asymptotes. That's something that we're skipping in this section. Okay, well, let's start at number 1 and let's look at end behavior. The way I've written this, the way I've given us f of x, that leading term is hidden from us. And so to find the leading term of the numerator, I need to take the largest power of x out of this binomial and cube it, because that will be the largest power of x to come out of that cubing. And so I'll have x cubed, and then multiply it by the same thing from the next binomial. I'll have x to the 1 from the x minus 3 to the 1, and then I'll have an x squared, and then I'll have an x squared from x plus 2 squared and x plus 5 squared, respectively. And then that'll be all divided by, I'll have an x squared to the 1 from the denominator here. I'll have an x to the 1 from my x minus 3, and I'll have an x plus 8 will give me an x to the 1, all multiplied together. All right, so what's that going to leave me with? I'll have, when I multiply exponentials of the same base together, I add the exponents, right? And so I'm going to have 3 plus 1 is 4. 2 plus 2 is 4, so I'm going to have x to the 8 in the numerator. X to the 8, and then that'll be divided by x squared plus 1 is 3 plus 1 is 4. So I got x to the 8 over x to the 4. Power in the numerator is greater than the power in the denominator. So I simplify this and I get x to the 4th, and then I have the end behavior the same way I used to get the end behavior for my polynomials. And so I have a positive x to the even, and that implies that I have this bowl-shaped graph, and then, whatever happens in the middle happens in the middle, but the left and right ends of the graph, they go up towards infinity. And so as x approaches negative infinity, y approaches infinity, and as x approaches positive infinity, y approaches positive infinity. And so we say our left end behavior equals our right end behavior equals infinity. Okay, and I really should color code that to be green again. Just using the blue to kind of remind us that that's a memorized fact that came out of our textbook or our lectures from earlier. Okay, now let's think about the y-intercept. The y-intercept, I want to evaluate f of 0. And so if I want to evaluate f of 0, what's that going to do? That's going to, every place I have an x on the right-hand side of this, I'm going to replace it with 0. And so what's that going to leave me with? That'll leave me, I'm going to cheat a little bit. I'm going to move you back over here because I've got the space and we're color coding so we can tell what's what. And so I got f of 0, and I'll have 0 plus 1 cubed. Then I'll have 0 minus 3, 0 plus 2 squared, and 0 plus 5 squared, all over 0 squared minus 25, and then 0 minus 3, and 0 plus 8. Straightforward but complicated. Make sense out of that, if you will. All right, so I have 1 cubed, negative 3, 2 squared, 5 squared, all over negative 25, which is 5 squared if I'm thinking about these things in simplest terms. And it's negative 5 squared, right? Not negative 5, parentheses, squared. And then there'll be times negative 3, and then times 8. But that 8, I could really rewrite that as 2 cubed, right? Because 2 squared is 4, and then 2 cubed is 8. All right. Well, writing this in terms of its simplest factors has helped me out, because now I can say I've got a negative 3 over a negative 3. I've got a 5 squared over a 5 squared. Now, don't lose that negative. That negative is still part of the game down there. Just like, well, okay, because these were both negative, that negative cancels. Because this is a positive 5 squared, and that's a negative 5 squared. Only the 5 squared cancels. The negative does not. And then 2 of the 3 2's cancels, and I'm left with a single 2 down in the denominator. And so this all turns into all of that work. Well, and when I cancel that 2, it's the 2 squared that cancels, and then just leaves me with a 2 in the denominator. So all of that work leaves me with negative 1 cubed, which is 1, divided by 2. And so my f of 0, which is my y-intercept. All right, so I know my y-intercept. I know my left and right end behaviors. And so now let's look for my x-intercepts. So if I'm thinking x-intercepts, that was set f of x equal to 0 and solve for x. But before I do that, let's simplify this function. because that's going to make both 3 and 4 a little bit easier, simplifying this function. Well, it actually would have made 2 a little bit easier, too. We could have gotten away with a little bit less math if we'd simplified first. All right, so if I do, how do I want to do this? Let's jump down to the next page. Give me a little more space here. So if I jump down, well, let's just jump down to here, paste this in. What I really want us to notice is that I've given this in mostly factored form. I've been a little bit sneaky. It's my job to be sneaky. Math is sneaky. The world is sneaky, so I got to get you ready for that. That x squared minus 25 is not fully factored. That's a difference of squares. And so I need to rewrite this whole thing one more time. I can take a look and see instantly that the x minus 3 over x minus 3, those will cancel. But nothing else immediately obviously cancels. And so by doing that, I already know that I have a removable discontinuity at x equals 3 because x minus 3 canceled out of the denominator. Was not left in. There's no vestige of x minus 3 left in that denominator. And so I note that I have a removable discontinuity, or a hole, at x equals 3. I'll have to find that y value later. Okay, now I've got x plus 1 cubed, x plus 2 squared, x plus 5 squared, all divided by, and this is going to be an x plus 5, x minus 5, because that's a difference of squares. Remember, this follows the pattern a squared minus b squared equals a plus b times a minus b. And so what we're doing here is creating that a plus b and that a minus b. Okay, and so now the x minus 3 is gone, and we've got an x plus 8 in the denominator there. Well, you're probably noticing that I have an x plus 5 in the denominator here and an x plus 5 squared up there. And so I should note that we have another removable discontinuity at x equals negative 5 for the same reasons. So another removable discontinuity at x equals negative 5. And that's why we had to simplify this thing. And so my f of x, my f of x that we're really finishing the sketch up of here with those discontinuities noted is x plus 1 cubed, and then x plus 2 squared, x plus 5, all divided by x minus 5, x plus 8. And let's make that 1 cubed a little bit more readable there. All right. Well, it's kind of nice. It's nice to know it's nice to know the simplified version of what we're after. Guess I never finished that off. Because when we want to solve this for our zeros now, if I go back to 3 here, all I'm really doing is when I set f of x equal to 0, I'm saying x plus 1 cubed times x plus 2 squared times x plus 5 equals 0, which is a good deal simpler than what we started with in the numerator. And I can, by inspection here, I can say that I have x equals negative 1 multiplicity 3, or x equals negative 2 multiplicity 2, or x equals negative 5 multiplicity 1 for my 3 zeros here. And you could break that into 3 equations using principle of 0 parts. X plus 1 cubed equals 0, x plus 2 squared equals 0, x plus 5 equals 0, and you'll get that exact same result. But since I was running out of space and we've done that many times, I was leave that to by inspection. All right, last piece of calculation that we need to do before before we try to sketch this is look at our domain restrictions. And we've already found that we have two domain restrictions, one at 3 and one at -5, and they're going to be removable discontinuities. And so when I talk about my domain restrictions, I already found that I have holes at x equals, what was it, -3? No, it was +3 and -5. X equals -5 and x equals 3. Now I'll need y values for those holes, and I'll just get them by putting 3 and -5 in for f of x. And so let's go ahead and just do that. So if I evaluate my y value here is going to equal f of -5, which will equal, if I plug all that in, we'll do it on this calculator. And so I'll have -5 plus 1 cubed, and then that'll be times -5 plus 2, and then squared, and that'll be times -5 plus, this is going to give me a 0, right? Plus 5, and then to the 1. Now we divide that by -5 minus 5, and then I need another set of parentheses here. Close that, because within that I need to now do times -5 plus 8. I'm going too crazy with my parentheses. There we go. That's what I actually want the denominator to look like, is two binomials multiplied together underneath a denominator, underneath a fraction, underneath the numerator. All right, so if I hit enter on that, I'm going to get 0 because of the whole, I've got the x minus 5 over x plus 5 in the numerator. And so I end up with a y equals 0 for this one. Now I'm going to go back up here and I'm going to reuse this calculation, save time, and instead of -5, I'm going to replace it with 3. You could also do this by graphing it and just looking at the value. But since we're trying to sketch the graph, I don't want us to look at the graph until the end. All right, 3, and then 3, and then 3, and that should, nope, we got a little bit more. Oh, that did wrap around. Good. That's what I thought. Which is a rather large number. And so we will talk about how to represent that kind of large number here in a bit. And this is one of the risks of making a crazy problem like this one. And so if I do f of 3 is going to equal that -582, we'll call it, -582. And so my y equals -582. Just because it's a large number, I always like to double check my typing and make sure there isn't a silly typo in there. But nope. No, that stands, and we get a very large number for that one. All right. Well, those are the coordinates for the two holes in our graph. There are two other discontinuities. The last two discontinuities we find by taking the denominator of our simplified version of our function, setting it equal to 0, because those are the non-removable discontinuities. These two discontinuities, they canceled out before we got to our simplified. So because the zeros in the denominator canceled out of the denominator, what that means is that every place other than 0, it was a number divided by itself, which was 1. 1 times the rest of this is just whatever the values of the rest of this are. And so any place other than 0, it didn't scale the value of my function at all. And at 0, it was 0 divided by 0, which is undefined, which is why it's a hole. It doesn't affect the look of the graph anywhere except for the place that it doesn't exist. Okay, so what we're looking for now are the zeros that are left over, because they do affect the scaling of my function at places other than their exact point. And that just means I need to take the denominator, set it equal to 0, solve for x, because that will give me all the x locations that cause me to divide by 0, that cause me to have a number over 0. And so if I have x minus 5 times x plus 8 equals 0, if I solve this and get x, well, these are multiplicity 1 zeros, right, because I have power 1 on each of those. And so I'll have x equals 5 or x equals negative 8, multiplicity 1, multiplicity 1. And what you really have here is x minus 5 equals 0 or x plus 8 equals 0. This is principle of zero products, because if x plus 8 equals 0, I don't care what the value of x minus 5 is. 0 times that value will equal 0, and this equation will be true. And so I can solve that separately. Same thing, same logic. If x minus 5 equals 0, I don't care what the x plus 8 is. 0 times that value will be 0. And so the x minus 5 can be solved on its own. Okay. And so now we have all the information that we need, because these are my vertical asymptotes, right? I should write it out. Vertical asymptote. I like to shorthand that VA. So got 2 vertical asymptotes, and then I have holes at those 2 points, and those are my discontinuities. The rest of this gives me n behavior, y-intercepts, and x-intercepts. And so I should be able to create myself a coordinate system here and start to fill in this information. All right, so if I start putting in some tick marks here, my y-intercept was at negative 1/2. All right, so I didn't need to go positive, I need to go negative. So 1, 2, 3, and then right here at negative 1/2, I'm putting in my dot for my y-intercept. My x-intercepts, because I find these things the easiest to put down on the paper, my x-intercepts were this -1, -2, and -5. Okay, so if I go back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, -5. And then what did I say? There's -1 and -2. So -1, oops, give me my pen back. -1 and -2. And so I just like to dot in a vertical line here to remind me that I have a vertical asymptote there when I'm graphing. And then at the bottom of that, I like to write in what the multiplicity is to remind me when I'm sketching in what the behavior around this vertical asymptote must be. I'm sorry, those are zeros. Those aren't VAs. What am I doing? This is why we have an undo button. There we go. Those were zeros. And so rather than dotting in vertical asymptotes, I'm just putting dots on the horizontal axis at those points. And these were all, these were various multiplicities. And so at -1, I have a mult 3. And so I kind of like to write M3 next to that. And then -2 was M2, I think. Yeah. And so I kind of like to write M2 and then M1, just to remind myself what these multiplicities are as I get into my sketching. My end behavior, left and right end behavior, are both infinity. And so over here on the left, I like to put an up arrow in. Over here on the right, I like to put an up arrow in, just to remind me where does this graph need to end up. And then I need to dot in those vertical asymptotes I was trying to do earlier. So 5, 6, 7, 8, negative 8, and I'll put in a vertical line, or dot in a vertical line, and call it multiplicity 1. And then I'll go over to positive 5. 1, 2, 3, 4, 5. And then dot in a vertical asymptote, and call that multiplicity 1. The only thing I haven't put on my graph are the holes yet, right? And so at negative 5 and 0, I have a hole because it doesn't actually exist at negative 5. And so my M1, 0 there, it doesn't actually exist there. And so I'm going to go ahead and erase that M1, 0. I'm going to go ahead and erase that black dot, if I can, without getting the line there. Excellent. And this is why we do these, all 4 of these, because sometimes you need to have a little bit more information about something that you've done. And so now I actually have a hole there. It's where it would have crossed the axis had it existed there, but it doesn't actually exist there. Okay. So the other hole was at 3, so 1, 2, 3, and then negative 500 and something, right? And so what I'm going to do with that is I'm going to put a break in my y-axis, and I'm going to put a tick mark down here, and then write negative 582, negative 582, and then put a hole down there. And now all of the information I've solved for is embedded in this graph. And I just have to figure out how to actually fill in the dots. Okay. I could start, and I think it's a reasonable thing to do, to start at either end, with either end behavior. And since we tend to think left to right, let's start with the left end behavior. How do I know that I don't start high and then approach that vertical asymptote like this? The reason I know that I cannot do that is because that causes me to cross this x-axis again. And I can't cross that x-axis without creating another 0. And I've already found all of my zeros, and I only have 2 zeros. And they're at those 2 points, and then a discontinuity that's going to cause me to cross the axis. And so before reaching this vertical asymptote, at some point, we don't know where, but at some point that turns around and starts approaching that vertical asymptote. Now, because this is a multiplicity 1 vertical asymptote, if it was an even multiplicity vertical asymptote, if it goes up as it approaches from the left, then it will go up as it approaches from the right. For an odd multiplicity vertical asymptote like we have here, M1, if it goes up as we approach from the left, then it must go down as we approach from the right. They go to opposite ends, if you want to think of it that way. If you have an odd multiplicity asymptote. And so I'm approaching that asymptote from the left. I come up here, and I remember this was a multiplicity 1, 0, or hole there, right? So I'm going to pass through the axis. Then this was a multiplicity 2, so I'm going to bounce off the axis. This was a multiplicity 3, so I'm not only going to pass through it, but it's going to look a little bit like a cubic as I pass through it. Now, what have I done? I need to pass through this, and yeah, it does look a little bit like a cubic as I pass through that. I'm not going to be too picky about that when I judge your rolls. Then it has to pass through my y-intercept there. Then it has to come down to this hole, and then from there, I know that it doesn't turn around and go up here because that would cause me to cross the axis again. And so it must keep going down and approach that vertical asymptote from the left going down to negative infinity. Because this is an odd multiplicity vertical asymptote, I must go towards infinity as I approach this from the right, because I went towards negative infinity as I approached it from the left, which is comforting because, and this is not a be-all, end-all, I've done this right, but it is comforting because if I had been supposed to start down here, then I would have had to cross that axis, which I can't do, and I would have known there was a mistake. And so it's not like I know this is right, but I do know, I'm not certain that I made a mistake. That's the most comfort I can take from that, is that I'm not certain that I made a mistake. And this is as good of a sketch as we can do given our algebraic techniques. Now, if we'd been given calculus, we'd be able to figure out where that turned around, where that turned around, where this turns around, where that turns around, and some of the extra behaviors in here, and some of the shapes of the function as it does these things. But we don't have calculus. We just have algebra. And for just having algebra, this is a really nice sketch of the behavior of this function. All right, moment of truth. Let's type this thing into the calculator and see if I've done this right. And so if I go up to the very beginning, because you always want to compare to the first problem statement, I've got parentheses for the numerator. I got x plus 1. And then I want to cube that. And then that's going to be times my x minus 3. And then that's going to be times my x plus 2. And then I want to square that. Whoa, what just happened? That's not what I wanted. Oh, yeah. Whoa. X minus 3, x plus 2. I want to raise that to the 2. Something funny happened there with my inputs. Delete that. All right. So now I've got parentheses x plus 5, and then we'll square that. And then go outside of that set of parentheses, divide, start me a set of parentheses for the denominator. Now for the first binomial in the denominator, I've got an x squared minus 25. Then that'll be times, and I'll have an x minus 3. That'll be times an x plus 8. Go to my window. We know this window isn't going to be right, but I'm just going to do a negative 10 to 10 to start out with. Negative 10 to 10, and we'll play with the window from there. Negative 10 to 10. The reason I want to start here is I want us to see the y-intercept at negative 1/2, and if we start with like that negative 581 on screen, we will never be able to see that value of 1/2 as it crosses the y-axis. So if I graph that, this is actually looking pretty promising. I don't see the things happening in the upper left, but I'm also only going up to 10, so I'm not too worried about that yet. If I zoom in on these, and I gotta zoom way in, I can see that this behavior is about what I said it was gonna look like. If I look at this negative 2 and 1, so if I zoom in, there's my negative 2 and my 1 zeros, and then remember I said I didn't know how tall that bump was going to come up to? Well, apparently it was extraordinarily short, right? Because we're talking like in the 5 thousandths range or the 2.5 thousandths range. But you also notice that I was right about the shape of it as it passes through that negative 1, that it takes on that cubic shape. Now, if I play with my scale a little bit here, I can see that my y-intercept negative 0.5 is correct. And so it's going through all those points that I said it would. And I also said we had no idea how high that bump was going to be. And so going up to 4, I put it around 2.5. Who cares? That we had no idea about that. And then going down from there, we'll try to keep our x-axis about the same and just bring the y-axis in. And if I keep bringing the y-axis in, hey, what do you know? We've got those two in the upper left and the upper right. They're just way up there, right? So they're huge, but they take on the shape I said they would. And if we zoom in on our x-axis here, you can see that -8 is where that vertical asymptote is. And you can see that if I keep zooming out on the y, that 5 is where that vertical asymptote is, which is, I didn't label it, but if we count 1, 2, 3, 4, 5, that's where I put that one, and that's where I said it would be from the math. And so this is another part of why I don't want you to run to your calculators when you're doing this sketching, because my sketch is correct based on what we know from algebra. But if you just put that into your calculator and all you see is this, you're going to write that down and you're going to think that those two things that happen in the upper right don't happen, and that this just keeps going on towards infinity, and that you'd call this, that the left and right in behavior would both be negative infinity here, and you'd be completely wrong. You'd also not, unless you played with the scales quite a bit, you would not be able to see where these zeros are. And so this is just one of those cases where we understand the situation significantly better than our calculators do. And us learning these techniques helps us to think significantly better than our calculators do. Because the way our calculators calculate these things is they just do a big table and play connect the dots after they've done a big table. And that's also why, no matter how much you zoom in, you're not going to see either of the two holes that I highlighted for us, the places where the graph doesn't exist. I don't care how much you zoom in here. I mean, we're at ridiculously tiny at this point. So we're talking about like what, 1/1000ths vertically, 10,000ths vertically. And I don't care how tight we zoom in on this, it will never show us that hole, because it's literally just skipping that point because it gets an error when it tries to do that calculation, and then connecting the dots through that point from the point before and after it. And that's just the way that most calculators do this. And so that's why it will never show you the hole, even though you know that it can't exist there. And so you can predict the function's domain restriction there, where the calculator does not. All right, I hope that helps us as we learn to sketch these things. And I hope it shows us a little bit of why we need to be able to sketch these things, is that it helps us understand the behavior of these functions as a whole even better than the calculator can help us understand the behavior of these functions.